first question is, how is a computing system realized? Traditionally, a computing system, a generic computing system, every computing system should be properly designed, properly engineered, and properly developed. Design means that the systems must fit some high-level properties, and these properties must be stated in such a way to be sound, not contradictory, and complete. Properly engineered means that the system needs to meet concrete efficiency or effectiveness goals. Or also properly engineered means also that the systems must be able to use acceptable resources, must be able to have an acceptable power consumption and things like that. Properly developed means that no implementation dependent deviations from these two specifications, the specification of the modeling, the specifications from engineered, must be fulfilled. So, this is about the design of a generic computing system. What about a secure computing system? By definition, computer security in abstract can be is the capability of a computing system of withstanding intentionally induced ill functioning. So, the crucial questions are: what in a secure computing system, what do we want to be secure, and against what do we want it to be secure? So, the answer to the first question in most cases is information. The information is the asset that needs to be protected. Ultimately, this means information means an hardware or software configuration or a piece of data. The answer to the second question, against what we want the system to be secure, means to identify the threats to the legitimate functioning of the system. And these threats can be eavesdropping, impersonation, forgery, tampering, malicious retractation of actions, induced denial of service, and so on. So, in order to design a secure system with resistance to these kind of threats, we need to specify, model the countermeasures to this threat as a satisfiability problem to some and identify some security properties. In particular, eavesdropping, the resistance of a system against eavesdropping, against the the copy of the data transmitted during a confidential communication, means to have a property called confidentiality. Impersonation and forgery means to have resistance to impersonation and forgery means to have the property that your system satisfies the property of authenticity. Tampering is bound to the property of integrity. Malicious retractation is bound to non-repudiation, and denial of service is bound to the concept of availability. So, how is a computer security realized? We realize a secure computing system, so a computing system which has all these properties, employing cryptographic primitives. Cryptographic primitives are the building blocks to deal with any protocol or system designed to operate in an environment absent of universal trust. So just to give a very, very general definition. So in other terms, employing a cryptographic primitive, we are able to provide confidentiality of transactions, authenticity of the transactions, Authenticity means that you are you are sure of the identity of your counterpart in a communication. For example, non-repudiation means that if someone sends you some data, this entity cannot deny in the future that the data has been received by you, has been sent. Okay. Integrity means that the data that you are accessing or you are transmitting cannot arrive to the other endpoint without changes, unauthorized changes. So all these kind of properties can be realized employing proper cryptographic primitives. So the next question is, where is cryptography really used? Where we can find examples of the use of cryptography? Basically, in every ICT, modern ICT service, HTTPS protocols employs in a transparent manner public key cryptographies and digital circuits. You can also encrypt your email, or you can encrypt your data and give them to a data outsourcing provider. You can find a lot of concepts about cryptography when you talk about electronic money, Bitcoin, or stored value cards, smart cards, electronic tokens, SIM cards, voice over IP, and so on. Okay. Most of the interesting thing in this nowadays is that most of these services are realized employing mobile devices, embedded devices. So all these devices, a SIM card or a smart card, a smart token, are all devices that can be seized by an opponent for even temporarily, and this attacker, this adversary can do analysis on these devices without any awareness of the legitimate owner of the device. Okay. So, what about cryptography? Cryptographic primitives are designed to provide security properties relying uniquely on the secrecy of a specific value, the secret key. Any other specification of the cryptographic algorithm, this means the algorithm itself or the other parameters of the cryptography or of the primitive, are publicly known. The only secret, the only unknown information is the secret key. So all the security of the primitive is based on this value. Cryptographic protocols are defined are communication or data processing protocol designed to fulfill some security properties. These security properties can be arbitrarily complex. Some of you can have heard probably to talk about proofs of computation or proofs of storage in the cloud. How you can be sure that if you put your data in the cloud and in the future you ask to the provider to retrieve some data, how can you be sure that the provider gives you all the data you need? So you can set up a cryptographic protocol that ensures you that the provider, the outsourced service provider, gives you a complete information about your data when answering your query. And you can do this employing a cryptographic protocol. Okay? So this just to say that the security the combination of cryptographic primitives can be arbitrarily complex to realize even high-level security properties. Okay. So, what about cryptographic systems? So, all is come to the design of a proper cryptographic system. How is a cryptographic system realized? The design of a modern cryptographic systems follows the same path of any other computing system. So we have a modeling phase, an engineering phase, a development phase. During the modeling phase, we need to prove the validity of some security properties from the assumption on the adversary knowledge. During the engineering phase, we need to model in the most faithful and efficient way the specification made, the results made, the results of the modeling phase. So, engineering phase, the outcome of the engineering phase is an optimized and faithful implementation of of the outcome of the modeling phase. Okay. Development phase means to implement the engineering design and tools, striving to prevent errors during this realization. What could undermine the design? We can have errors in every phase. A modeling error means that the adversary model that we devise may not be fit to represent the actual capability of the adversary. For example, the adversary, when observing the use of a cryptographic primitive, knows obviously the inputs and the outputs. What he doesn't know is the value of the secret key. But this notion is also called security at the ends, because the adversary is able to see what are the inputs and what are the outputs, may not be sufficient, because the adversary may collect also some other information, additional information, about the inner functioning of the device, about the inner functioning of the device. For example, the power consumption, the electrical current absorbed by your mobile phone can be can leak information about the values of the value of the secret key. In a moment, we'll see how. We'll see some examples of how this is possible. But a modeling error, the most common modeling error, is a modeling error in this sense. Okay. Engineering errors means misinterpretations of the intentions of definitions of these of the higher level design. And an engineering error can be a logical flaw, so basically a misinterpretation of the modeling, or the modeling phase, or an unintentional, not intentional side channel leakage. So the implementation of the cryptographic primitive can be designed at an engineering level with some errors on the without taking into account all the details of the underlying computing platform. The architecture, the hardware architecture, if you don't take into account the hardware architecture of the the hardware architecture of the device where the cryptographic primitive is run, some side channel information may leak during the execution of the cryptographic primitive. Okay. Finally, the development errors refers to development errors refers to carelessness or lack of experience or excessive freedom to implement that leads to implement a non-faithful or unreliable project results of the engineering phase. Obviously, every phase, modeling phase, engineering phase, development phase, can be affected by human errors. Okay. So, how we can, how currently modern cryptography employs what is called a cryptographic engineering design process. Cryptographic engineering design process focuses on the importance of the implementation aspects at each step of the design phase. In particular, as a premises, we need to consider that the secret key is stored into a device in a non-readable way. And embedded or mobile devices that are seized by an opponent, even temporarily, represents a quite common scenario. With the Internet of Things, with the widespread diffusion of embedded devices, this kind of scenario is quite common. It's a real threat. Okay. So basically, cryptographic engineering consider doing a proper cryptographic proper cryptographic engineer design means to consider the details about the implementation also at level of modeling. Okay, so at this level, a cryptographic engineer consider the security of the device not only at the ends, but also he considers also the details about the inner functioning of the device. The other thing a cryptographic engineer takes care is the efficiency of the implementation, because the detailed knowledge of the executing platforms allows to trade off the power consumption, the execution time, and all these, or also it takes to it allows to trade off an hardware implementation versus a software implementation, or a mixed one. So, so considerations about performances, energy consumptions, or area of the silicon area of your device can drive you, the designer, to choose an ASIC or FPGA design or a software implementation, or both, a solution which is in the middle of these two kind of extreme. Okay, so let's see. What about knowing the details of the implementations means to be aware of the so-called side channels. What are side channels? Possible side channels are the power consumption of the devices, the electromagnetic emissions of this device, the execution timing of the device. You can measure the behavior of your application, measuring the timing of every run, acoustic emissions or faulty results. When you have an embedded device in a low-cost, low-budget laboratory, you can easily measure the power consumption or the electromagnetic emission of every embedded device. So just to see how these side channels works. A power or EM side channel attack, in principle, consider an adversary as a perspective of the adversary. This one. The cryptographic implementation executes a known cipher with known inputs and outputs. The attack exploits the key dependencies in the data flow of the algorithm. This means that assume for a moment to employ a block cipher, DES or AES, so asymmetric key cipher. Asymmetric key cipher with an n-bit secret key. An exhaustive search for the correct key value would take 2 to the n trials. If n is sufficiently large, this is impossible to perform. Okay. From a side channel aware adversary perspective, the adversary obtains information on a single intermediate operation of the cipher involving only a few key bits, X key bits. This is because we assume that the adversary knows everything about the algorithm that the device is executing. And for example, a software implementation will employ the secret key, a 128-bit secret key, only a word at a time. So we have that a single operation, a single intermediate operation of the cryptographic algorithm, will say a XOR operation or an addition operation, will employ X key bits with one word of the input values. So the adversary can obtain can select to attack a single intermediate operation of the cipher. Knowing the non-key inputs of the operation, the adversary can predict the side channel behavior for all the values of the X key bits. So, and as a third step, this adversary can compare the predictions against the measured behavior. So the correct value of the X key bits can be found looking at the best match. Okay. So just the typical workflow of a power-based side channel is this one. We have a cryptographic device with a non-readable key stored inside it. We have an oscilloscope, and we know the inputs of the algorithm. Knowing the inputs, we can build a power consumption prediction for every possible value of a portion, of a small portion of the key. Then we can correlate with a statistical test the measurement about the power consumption of the device with this power consumption prediction. And finally, the best match will give us hints about the correct value of this portion of the secret key. So for example, consider an exclusive OR I instruction involving 1 byte of the key. Given a set of input values, the adversary computes a power consumption prediction for this instruction for each possible value of the key. For example, the power consumption of a CMOS-based device depends on the switching activity you have into hardware registers. So a simple model of this switching activity can be realized counting the number of bits that are equal to 1 as the results of this operation. If you have an instruction that computes an exclusive OR between 8 bits of the key and 8 bits of the input value, you can compute the Hamming weight, the number of bits equal to 1, of every possible outcome of this operation, varying the values of the key. Okay? You know the inputs, and you can brute force every possible value of this 8-bit key. Okay? Then you can correlate all these predictions with the actual power consumption. So the prediction fitting best, the actual measured side channel, which can be the electromagnetic emission or the absorbed power consumption, is the one based on the correct key guess. Okay. So another side channel is the time side channel. And also simple power analysis is the functioning of simple power analysis techniques are like this. The adversary perspective in this side channel is that the cryptographic implementation executes a known cipher with known inputs and outputs. The attack exploits the key dependencies in the control flow of the algorithm. Consider, for example, this pseudocode. This is the pseudocode of a schoolbook RSA implementation. The input message is M, the secret key is D. If you look at this pseudocode, depending on the value of the highest bit of the secret key, each iteration of any iteration of this cycle executes an additional multiplication or not, okay, depending on the value of every bit of the secret key. So the multiplication in the if construct is performed only if the secret key bit is equal to 1. This means that if you are able to measure either the execution time or the power consumption during the execution of the algorithm, you are able to distinguish if in a certain instant of time a further multiplication has been performed or not. Just to give you an example here. If you measure the power consumption of that schoolbook RSA implementation, you'll see something like this. This is one power measurements, the power consumption measurement of a single execution of that algorithm. And how you can see, you can bind each feature to a specific operation. So looking at this, you can derive easily the secret key. Okay. So instead of looking at the power consumption, you can also use the time side channel, because performing an additional multiplication will take more time. Okay. So another quite popular side channel is the acoustic one. The acoustic side channel is the same that we have just seen, but over the acoustic mean. In practice, with this kind of attacks, it is possible to hear via an ultrasound microphone whether or not the RSA conditional multiplications are performed. How? The crucial observation of the authors of this kind of attack is that the capacitors of the switching mode power supply of your laptop are induced to whistle in a narrow, high audible, low ultrasound range due to the electrostriction phenomenon in the capacitors of the power supply module. Okay, depending on the different instantaneous energy demands of the RSA execution. So if you execute a further multiplication in the algorithm, the whistle of the capacitors on your power supply, on your laptop power supply unit will be different with respect to the one that you can hear when you are not executing another multiplication. Okay? So this is basically, in a nutshell, the idea of the acoustic side channel. It's the same idea of the timing-based one, but over the acoustic mean. Okay? Finally, we have fault-based side channels. The idea is that the attacker, in this case, is not takes an active rule, and he can exploit transient alteration in the computation of the cryptographic algorithm to create a faulty outcome which leaks information on the secret key when you correlate the faulty outcome with the correct one. So some examples of fault induction techniques. Inappropriate power supply. If you have a mobile device, you can always underfeed your device, the voltage supply of your device. You can easily also induce voltage glitches in on the functioning of your device. All this kind of tampering will lead to logic gate to slow down the switching activity of logic gates, of the transitions performed by signals during the logic in the logic of the circuit. This means that if you do something like this, some bit values will be saved before they are stable. So if you underfeed your device, you'll have what is called a setup time violation. So when some values must be stored into a register, the correct value is not stored properly into the register because the signals is not fast enough to reach the register. Yes, okay. Another fault induction technique is inappropriate timing. Most of the embedded devices are clocked externally, so you must supply the signal clock. So you can overclock the circuit to cause other setup time violations in a controlled manner. So if you are able to induce this kind of errors, you can look at the erroneous output and look also at the correct one. And you can be able to correlate these two information to derive the secret key. Okay? So this is basically an overview, a very fast overview of cryptographic engineering and side channels. Just one case study, just to give you an idea of what kind of investigations can be performed on this topic. In this work, for example, we concentrated in this scenario. We observed that a number of commercially available embedded systems and contactless devices, like smart cards, RFIDs, and so on, are equipped with 8-bit, 16-bit, or 32-bit microcontrollers. The security services on these devices are obtained through software implementations of elliptic curve cryptography. And in particular, the security services on these devices consists of a digital signature realized through this kind of primitive. This is a standard digital signature primitive, elliptic curve digital signature algorithm. So we decided to assess the fault vulnerability of the ECDSA software implementations on this kind of platform, on single cores microcontrollers with 8-bit, 16 bits, or 32 bits word length. The results that we have obtained is that we defined a novel fault model for this signature algorithm. A novel fault model, we observed that if you are able to induce an error in the results, in the computation of a single digit of a modular multiplication, you can be able to recover the secret key. So I'm not giving you the details of this fault model, but the basic idea is that if you are able to induce an erroneous computation even in a single digit during the computation of a multiplication, you can be able to exploit this to recover the secret key. How to obtain this kind of error? This kind of error in the results of a modular multiplication can be obtained via clock glitches, power glitches, or constant voltage underfeeding. And this kind of error is able, ultimately, to reduce the security of this algorithm very much, to the point that the problem, the values of the secret key can be brute forced one piece at a time. Okay. ECDLP here refers to the elliptic curve discrete logarithm problem. This is the discrete logarithm problem is the mathematical problem behind this kind of primitive. And if you are able to inject this kind of error, you are also able to solve this mathematical problem in an easy way. Okay. Okay. So from a cryptographic engineering point of view, the other fundamental results has been that has been also the proposal of a fault-secure HDSA algorithm able to ward off all currently known fault attacks with performance overhead less than 30% with respect to an unprotected implementation. This because less than 30% overhead is quite acceptable as an overhead for an embedded device, because on embedded devices and portable devices you do not have high throughput constraints. So if you are able to engineer a solution that does not double the execution time of the algorithm, this is quite good and acceptable in commercial application. Okay. So I think I said too much. So and if you are interested, I can give you also details about other possible countermeasures. Another topic we dealt with is the design of countermeasures against power-based side channel attacks. And in this scenario, the execution of software implementation of block ciphers we consider the execution of software implementation of block ciphers on portable devices, equipped again with a low-end microcontroller. The objective of this work was to design an LLVM compiler extension able to secure any block cipher implementation against this kind of attacks. The developer, in extreme summary, the developer decorates the C code portion of your cryptographic algorithm with a custom keyword. For example, he can put before any before the subroutine that computes the AES this keyword. And then the compiler provides a side channel resistance object code corresponding to the marked code portions. Okay? So it's the compiler that during the translation from the source code to the binary code put into effect the countermeasures against this kind of side channel. Okay? Each sensitive binary instruction of the cipher implementation takes as input a small portion of the key and a known value derived by the cipher input, as we have seen before. And just a quick recap, the typical attack workflow is that the attacker selects a sensitive instruction and builds a consumption hypothesis for each possible value of the secret key portion. The attacker measures the power consumption of the target device during the execution of the cipher, and for a statistically significant number of times. The attacker correlates the measured power consumption with the consumption hypothesis formulated on the possible values of the key portion. The best match will correspond to the correct value of the secret key portion. So, given this workflow, the principle of the MIT countermeasure is to change the side channel power profile of the cryptographic code at every run of the cipher. How we obtain this? We replaced the execution of each sensitive binary instruction with a different but semantically equivalent code fragment at every run of the cipher. For example, you can substitute a XOR operation between these two values, register 0 and register 1, with the Boolean formula corresponding to the exclusive OR operation or operator. Okay, and you can substitute this. This is only one possible replacement, but you can easily imagine a lot of semantically equivalent code fragments equivalent to this operation. So every time you run the cipher, you execute a different code fragment. In this way, the measurements of the adversary during the run of the algorithm will refer to each time will refer to a different algorithm. So it is impossible to reconstruct, to lead the attack. Okay. So just to give you a conceptual model. So in the typical pipeline of a compiler a compiler framework. In a compiler framework, you have the source code, a compiler front end, which translates the source code in an intermediate representation. This intermediate representation is optimized by the intermediate modules of the compiler. The optimized intermediate representation of your program is put as input of the backend of the compiler when you have the translation between the intermediate representation and the object code. And finally, you obtain the machine code. So we modified these two steps, the compiler front end and the optimization modules of the compiler pipeline, to obtain this kind of behavior at runtime. At execution time, you have that when you run your algorithm will execute some non-sensitive instructions. And when a sensitive instruction must be executed, this sensitive instruction is translated as an equivalent code fragment, different every time. And the execution of the algorithm continues in this way. Okay. So this is another example of a work dealing with a cryptographic engineering problem. Okay. Okay. That's it. Thank you.